Okay, so hello everyone. You are welcome to today's lesson. And today's lesson is going to be the continuation of where we left off under our lesson titled Probability. So this is the topic that we are looking at. In our previous lessons, we looked at how to solve simple probabilities. Okay, after learning or getting to know the definition of probability and all the terms that you are likely to encounter, they are corresponding words meanings. Okay, and if you remember when we were looking at the types of events, I mentioned but a few. Okay, and I told you that we have others that I have intentionally shelved because those types of events are special events which we will look at, okay, in the near future, and we have the near future in front of us. Okay, so another type of event will be complementary events. Okay, and remember, I've told you set and probability, okay, very, very connected. And you know, we said that in terms of probability, okay, probability, if you have set, it becomes, okay, event. So indirectly, it is complementary what sets. Okay, only that set and the probability, okay, will be what event. Am I clear? Hello, are you with
Yes.
me? So you know, when we are dealing with what set, so let me start from that perspective. That is the from the known towards the unknown. Okay, so quickly let's look at, okay, what we have here. In set, you know, when you are asked to find the complement of a set, okay, how do you find the complement of a set? Any ideas? If you know that complement of what? Of an event or complementary event should be very easy for you. So quickly, we have a lot to do. So if you know, please put up your hand. Okay, I will give you the opportunity to talk. Okay, Lorraine.
Is the complements of a set is the elements of this set that are not found in a universal set.
Very good. Perfect. Awesome. Okay, so with this, you can see that you cannot get the complement of a set without knowing the universal set. Is that clear? Because its definition takes its source from what? The universal set. Without the universal set, there is no complement. So in the same way, okay, you can see that when it comes to sets, what did I tell you, okay, is the name given for the universal set and the probability. What is the special name given to the universal set when it comes to probability? Hello, my professors, you know I always want my class to be interactive, especially when you people are smart. Okay, special name. Oh, really? Oh, you are saying that, Mr. Hackman, this is so trivial. You want us to answer this question? Okay, I've told you we don't trivialize any question. So I'm waiting. Oh, not even a single person. Then I'll start mentioning names. Okay, Evelyn, let's go. What's the special name given to universal sets when it comes to probability? Even today, I've mentioned that. Let's go, Gloria.
Please, I'm not so sure, but I think it's sample space.
Oh, you should be sure because I've taught you. I gave you all the connection. I told you that sample space is for universal sets. Okay, sets will be events. Okay, elements will be outcomes. Do you remember? All the definition I made you aware that there is a special connection with the set. So if you know that of what the set, you should know that of what of the probability. Okay, anyway, very good. So it will be the sample space. So it means again, okay, because we are dealing with events, okay, which basically will be sets anyway. okay, with a special name. When you are defining complementary events, okay, you have to define it relative to our universal set and the probability, which is for the sample space. So in the same way, let's move from the set perspective. If you have your universal set, okay, mu, okay, to be made up of 1, 2, 3, maybe 4, and I have my set A to be what? Maybe 2, 3. Okay, what will be my A complement? Okay, this one all of us should know. Okay, so let's go together. A complement will be
1 and 4.
1 and 4. So you can see that if you look at it critically, okay, A complement is equal to not A. Can you see that?
Yes, please.
So not A, but in the universal set. As simple as that. So anytime you are talking of complement, it's the negation, okay, of the set. That's all. That is not. Anytime you attach not to anything, you are negating it. So it will be your universal set minus what? The set itself, and that will give you your the set complement. So in the same way, here in terms of probability, what you have here will be an event. So the A that you have here is an event, it's not a set. Okay, so it's a set with a special name, event, and this is what the sample space. So the complement of an event A, okay, will be what? Not A, which is the same as your universal set, which is the sample space, minus what? The set itself, which is what? The event. As simple as that. So quickly, let me read what you have here, and you can see that we get the meaning of exactly what is here. So the complement of an event refers to the members of a sample space not present in the event. Okay, and this is very clear. Therefore, the complement of an event E is the event, not E. Exactly what I just said. Okay, it is denoted by, okay, usually in maths, okay, the set or in set, to be more precise, you have only one. You use this, we usually use this. Okay, however, in probability, we have two more. Okay, I wrote only two, but there is an extra one which I decided to not to add it, so that those who will not come to class, they will not, okay, get to see that or know that unless they watch the video. Okay, so in this case, what do we have? We are going to have another one which will be maybe A bar. Okay, that is another way of representing or denoting, what do you call it, as the complement of a set. And we also, or the complement of what? An event. And we also have A to the power C for complement. Okay, that's the one that I left out here, which is intentionally though. So here, this will be the two ways. E bar, and I always tell my student that the bar that you have the indirectly is negative. So it means take out what? Your sets from what? From the universal set, or take out what? The set of possible outcomes in the event from the sample space, and that will give you the complement of the events. That is if you know the outcomes making in the sample space. Okay, however, after knowing complementary events, every complementary event, okay, must follow the rules that you have below. Okay, and the major rule is what I have highlighted in red here. Okay, and the major rule is that the probability of any event and its complement, that the sum of the probability of the event and its complement, should always give you 1. Always, and very soon you will know. Okay, we'll demonstrate that using a particular event. Okay, take note of that. However, you can see two more, okay, rules. However, these two rules that we have here, again, okay, we had them derived from this. This one is when you make the probability of the event itself the subject. So you have to move this one to the side, which will give you 1 minus the probability of the complement of the event. Is that clear? Is my point well made?
Yes.
As for the example that I've stated here, you should be able to deal with it. Okay, with the fact that if the event A is getting a 3, then the event A bar is not getting a 3. So you should know. And with this one too, it will be when you make the complement the subject. Probability of the complement the subject. So if you move that one here, you get it. So the last two that you have here is trying to tell you that if you know, okay, the probability of the complement of an event, you know the probability of the event itself and vice versa. If you know the probability of the event, you know the probability of the complement of the event. As simple as that. So in certain situation, you will need, okay, what we have here, these formulas that we have here, which I said basically is coming from this major rule that you have there. Okay, any question before I move on? We are all fine. This explanation okay?
Yes.
Very good. Okay, so now let's move on to our next. Okay, and this will be more or less an illustrative or worked example. So worked example 1, find the complement of the following events. Okay, we are finding the complement of the events that you have there. A, tossing a coin and not getting a head. B, rolling a die and getting an even number. Then C, selecting a letter from the alphabet and choosing a vowel. Okay, so quickly, let's go and have a look at what the solution. So let's go and do or present the solution together. Okay, so let's look at A. So the question is what you have here. Okay, if you read the A, you can see that the A is made up of what? When you are tossing a coin, what exactly are you doing? In terms of probability, what is the name given to this activity, tossing a coin? Okay, what is the name? Remember, we are revising basically. As and when we get to where I want you to make me proud, I will fall on you. If you are looking at the activity of tossing a coin, what is the name given to that? Oh, I introduced you to the terms and I made you aware of all that I'm asking. Any ideas?
Heads,
Come again.
heads and tails.
No, heads and tail will be the outcomes. But I'm looking at the activity of tossing a coin itself. Oh, I gave you a simple
Is the event.
event. Not exactly, no. Anytime you are performing an activity, okay, and the probability, we give it a name. Okay, the last try. Come again.
Outcomes.
Outcome. The outcomes will be the results. No. Wow. Oh, have you forgotten trial? Have you forgotten?
Random experiment.
Experiment. Okay. It's an experiment. Okay, anytime and you are tossing a coin, we are dealing with a trial, you are performing an experiment. Okay, so you can see that in this statement, you can see more or less a trial or an experiment, and getting ahead will be your event because a certain result will come. You get it? So you get a set, and that set will give you your event. Is my point well made? Because if you don't perform your trial or your experiment, definitely outcomes will not come. There wouldn't be any outcomes. You get the point? Okay, so this is it. So here, let's see. So you can see that always, if I say the event E and not E, the not that you are going to attach, okay, you attach it to the event. You cannot attach not to the trial. So I cannot say not tossing a coin. If I'm looking at not tossing a coin, then it means definitely there wouldn't be any results. Okay, for me to get outcome and therefore use the outcome to get my sample space and use it to get my event itself. You get the point? So when you are writing the complements, okay, of what you have here, and I want it to be in terms of, okay, statement. Okay, I can write it this way, and I have two ways. The first direct statement, remember I've told you that anytime you are dealing with complement, it's not the event. So here I will look at tossing a coin, so I can write therefore, okay, tossing a coin, I'm writing the answer. Tossing a coin, Okay. And okay, the initial one was getting ahead. So this time around it will be not getting ahead. You get the point now. Hello, are you with me?
Yes, please.
Okay, so can I also say that this statement that I have here is the same as or tossing a coin, okay, and okay, getting, if you are not getting ahead, what will you get? A tail.
A tail.
So that's also another way, and we are all right. You get it? Did I hear no?
Please, can you go over?
Okay, all right. Okay, so from where exactly do you want Mr. Hackman to go over?
Please, starting with the solution.
Come again, the second one.
The first one and the second one.
First one, okay, all right. So we are looking at, remember, the complement of any event is not the event. Is that not it?
Yes,
And I said that if you read the statement that you have here, okay, this statement basically is coming from two simple sentences: tossing a coin and getting ahead. Okay, I mean getting ahead. Join with what? End. You get it? So the first part of the statement is this is not an event. Tossing a coin, can it be an event? Remember, I said there is a trial or an experiment. Getting ahead is an event because okay, ahead will be an outcome. Every event will give you an outcome at least. Okay, tossing a coin is not an outcome. Getting ahead is an outcome. So it means this is your event. And the complement of an event will be not the event. So once you are able to get the event out of, in the statement, you just attach not to that event. So this will mean once we are able to see that this is the event in the statement, then it will be tossing a coin and not getting ahead. That's the complement of this statement A, which we said is the same as tossing a coin, and if you are not getting a head, you will get a tail, and getting a tail. Is it clear now?
please.
Okay, very good. Okay, so now we are going to look at the B. Okay, so let me see if the explanation that I've given so far is well understood. Okay, someone should give me exactly what he or she will write, okay, for the B as the solution.
Rolling a die and not getting an even number.
Perfect. Okay, so rolling a die, you cannot attach not to it because it's not an event. It is a trial. So rolling a die, okay, and not getting, okay, an even number. Okay, Paula.
Rolling a die and getting an odd number.
Perfect. That is also another way of saying it. You get it? So that also falls in place. Or rolling a die, you cannot do this. Please take note. Okay, and okay, getting, okay, an odd number. Is my point well made? Oops.
Yes.
Okay, all right. So the last one, you all say it. Okay, and let's see. Okay, so first of all, in the two statements, okay, tell me the one that will be your trial or your experiment. The C, the statement C. Okay, give me the statement that is telling you your trial.
Selecting a letter from the alphabet.
Perfect. And what will be your event?
Choosing a vowel.
Choosing a vowel. As simple as that. So in this case, okay, what will be the complement? I want the one with the knots before we come to, okay, deal with the knot to make the other direction. So if you want to attach the knot, how would the statement read in terms of the complement?
Selecting a letter from the alphabet and not
Choosing a
vowel.
vowel, which is the same as what? Selecting a letter from the alphabet and choosing what?
A
A
consonant.
A
consonant. Got
consonant.
it.
As simple as that. Okay, so you are doing well. Keep it up. Okay, so now let's move on to our next question. Okay, so this is what we have here, and this question, after doing it, you realize that the rules that you were given in terms of the complementary event rules, very, very solid, valid. Okay, so quickly let's look at, so a number is chosen from what you find the probability that the number is A even, B not even. So immediately you see not, then obviously you know that we are talking about what? The complement of what? This. You get it? Odd, not odd. Prime, not prime. So it means if you know one indirectly, you know the other. So we'll use or treat the question as if we are not aware of the connection between complementary events in terms of the rules, and deal with it our usual way and see whether you end up getting the same result after using the rules. Okay, so let's look at the solution. Okay, so solution, a major number. Yes, there is a major number, and the major number there is what? 1. Okay, so let's look at what question, question 2, forgive me. So 2. Okay, now what are we giving? We are giving the set, and you know that the set will be your sample space. So your sample space S will be equal to 1, 2, 3, 4, 5, 6, 7, 8. So that's what you are giving. Okay, so what are we supposed to find? A, we need to find P number is even, or P even number. Is that clear? So I'm going to write therefore here. Okay, and have P, my event is what? Even number. That is getting, a number that is what? Even. So in this case, this is what we are going to do. Okay, you go to your sample space and you go and pick your events. Okay, the number of what? Events. The number of outcomes in the event. So we are looking at what? Even numbers. How many even numbers can you get from the sample space?
4.
4. 2, 4, 6, and 8. So it means your number of successes, will be 4. So we are using our basic, probability formula over your sample space, the number, and that is 8. Okay, this can be reduced. Never leave it like that. So always reduce. So that gives us 1 out of 2. Is my point well made?
Yeah.
Okay, very good. Now B. Okay, we are looking for therefore P, not even. Okay, so what would that be? Okay, let me write not an even number. I'm waiting. Count the non-even numbers.
4.
Okay, you get what? 4. Do you agree? Okay, so 4 out of what? Again, a total of 8, which gives you what? 1 over 2. Is that clear? Okay, very good. Now, this is it. Okay, with this approach, you can see that you relied, strictly on the sample space, and you counted your number of successes, and therefore divided that by your number of elements in the sample space. However, let's look at this odds. The alternative method. You want to use the rule. Okay, you know that if you know probability of any event, you know the probability of the complement. So if you are finding P not even, this will be equal to 1 minus P even. That is the probability. You remember the formula?
Yeah.
Which will be equal to 1 minus, what did you get for P even? 1 over 2. And that also gives us 1 over 2. So you see the validity of that formula. And this one, you could use the first approach because you knew the outcomes. Okay, however, if you don't know the outcomes and you just give you the probability straight away of one of them, you are left with no other option than to use the connection here. Okay, so we are going to see the other one too, and let's see. Okay, and again, I think, okay, BK, when I move on, I will come back and we'll look at that. Okay, so let's look at the C and D. Okay, C. What are we looking, okay, for? We are looking for P, okay, not, oh, sorry, odd rather, forgive me, odd number. Or if you like, you can write P odd because you know you are dealing with odd numbers. Only that you have to be a little more specific. So that will be equal to, you go and count the odd numbers, which will still give us how many? 4?
4 on 8.
Okay, so 4 on 8, very good. Which also gives us what? 1 on 2. Okay, so here, my D. Okay, remember, anytime you are moving from a sub question to another sub question, leave a line. And that's the only time you leave a line. When you are solving, never leave any space between your steps unless you are moving from a sub question to another sub question. And I'm saying this especially to those who, okay, are joining us for the first time. Okay, so now what do we have? Therefore, okay, P not, okay, odd, okay, will be equal to, okay, so what do we have? You can use the same situation. However, I want to use the formula, and that will give me 1 minus P odd. Okay, which will be equal to 1 minus 1 over 2, which will be what? 1 over 2. Is that clear? If you use the other approach too, you get 4 over 8, which will reduce what? To 1 over 2, the same thing. Okay, as simple as that. Now let's see. Okay, we also made the major rule. Okay, we said the probability of what? The event plus the probability of its complement, okay, should always give you 1. So now let's see whether probability of the event, which is what? Even. Okay, plus probability of the complement, which is what? Not even. Okay, will give us what we are looking for. So P even gave us half, am I right? Plus P not even also gave us half, which is equal to 2. Sorry, which is equal to 1. Is that clear?
Yes.
Okay, and if you do the odd and not odd too, you get the same thing. Okay, it will be half plus half. Okay, now let's look at mentally, let's look at the E and the F. Okay, P prime. Okay, how many prime numbers do you see here? 1 is not prime, so it will be 2, 3, 5, and 7. So that will also be 4. Is that not it? Am I right?
Yes.
Okay,
Yeah.
so it will be 4 on 8, which reduces what? 1 over 2. Okay, that is the for the prime. Not prime, let's see. Okay, 1, 2, 3, 4. So also will give you 1 over 2. Okay, if you count. However, if you use the rule, it will be 1 minus P prime, which will be 1 minus half, which still gives you what? Half. Hey, Rabna, are you fine?
Yes.
Great. All right. Okay, so now let's move on to, okay, our next what question. So question 3. The probabilities that Ama and Kweku will pass an examination, okay, are 0.7 and 0.8 respectively. Okay, find the probability that Ama will not pass the exam. So once you see not, then it means it's negating a certain statement, and that will bring about the complement of that statement. You get it?
Yes.
Okay, and in this question, do you know the sample space? You don't know the sample space. So if you want to rely on the formula itself, and the formula talks about the sample space because you need to know the outcomes and what have you. This one, no, you cannot use that technique. So whether you like it or not, you have to learn how to use, okay, the relations between the probability of each event and, okay, the probability of the complement of that event. So quickly, let's look at how best we can present our solution to this question. So this is it. So solution to question 3. Okay, so question 3. Okay, what do we have? So, okay, probability that Ama Kweku will pass an exams. Okay, so this statement I want to avoid. Okay, a whole lot of them, and I want to write less. Usually, when you encounter this situation, okay, if you like, you have two ways of presenting your solution. Okay, I will give you the ideal way that we expect you to present your solution. So always make sure you get a representation for the positive events. So now let's see. My first event, and I'm going to events are denoted by letters, capital letters for that matter. Okay, so my A, I want to use AMA. So A will be equal to, I'm looking at my event, okay, that Ama will pass an exam. So I'll write Ama, okay, will pass, okay, an exam. Okay, so examination. Okay, comma. Once I represented, okay, Ama will pass an exam by A, then definitely I will go for K for Kweku. So I'm going to use K to be equal to what? Kweku, okay, will pass. Okay, so this is what we have. Okay, so now that I've done all that I'm supposed to do, if you read the question carefully, you can see that you can extract the data. So this implies that, okay, P A. You remember you've been given the probability that Ama will pass an exams, and that is giving us what 0.7. I hope you are following. Very soon you see the relevance of the representation that we have here very soon, why it is critical. Okay, and what else are we giving? PK, and K is what? Okay, Kweku will pass the exam. So probability that Kweku will pass an exam is also giving us what? Okay, 0.8. Is my point well made? Remember, it's the same, similar to sets. Okay, similar, where if you are given a word problem, get your representation, then move on. Only that with this one, you don't put this in brackets. Okay, because you don't know the outcomes for you to find a number. Where you know the outcomes for you can find the number is given, then you can label that as a set. Otherwise, don't put it in curly brackets. Is my point well made? Or I should come again? Okay, I said you can see that, okay, my representation, I didn't put Ama will pass an exams in curly brackets. Same as Kweku will pass an exams. Okay, and I said it's just for this simple reason. Okay, because in the question, you don't know the number of A, and therefore, so you are not given anything concerning numbers. If you are given anything concerning numbers, then it means what you had there was a set. It is a set that we can get the number of elements in the set. So if you are not given the numbers, okay, your representation, never put them in brackets. However, if you are given the numbers, you put it in brackets. Maybe you were told that a box contains 8 red balls. Okay, you are dealing with what? Numbers. So I can let B to be what? My red ball, and therefore write the number of red ball. But my B, which I'm defining, must be put in the curly brackets because it's a set that I can find its number. You get the point? With this one, you can't find the number. Okay, so curly brackets will not be necessary. You don't attach that. So now to the actual question. So A. Okay, what are we supposed to find? P, so let's write P, therefore P, and you write Ama will not pass the exams. And please take note, you can use the complement. Okay, however, I'm talking about maybe a complement here, but because you are writing therefore, don't come and write a complement here, because you don't conclude with what you introduce. Is that clear? You introduce A, somebody could have used M, somebody could have used X, what have you. you introduce A, and in math, you always avoid concluding with what you introduce. So this is how you proceed. Because your conclusion, you conclude with exactly what you have here, or maybe a better, okay, a more precise and concise form. But here, we cannot write it any better than Ama, okay, will not, okay, pass, will not, okay, pass, okay, the exam. Okay, and you close it, and this will be equal to, will not pass. Remember, it will be 1 minus P Ama will pass, which is A. Do you agree? So you can see that if you didn't write you didn't define, here you were supposed to write the whole of P probability of Ama will pass the exams there. Okay, you could have written that, the whole of that. So here you save a little time. And because the question, okay, more or less, okay, not one. If it's only one, then you could have started by saying, given P Ama will pass an exam. So you could have started by saying, given, okay, P, what you are giving here, probability that Ama will pass. And you write in brackets, Ama, okay, will pass the exams. And, okay, P, okay, Kweku will pass the exams. In that case, you don't get your representation. Then you can write, this implies that, okay, P, so you are now going to write the whole of that statement again. It will waste your time. So usually, get your definition, because at a point, you will need your representation. So at this point, what do you write? 1 minus P of A, which you know, 0.7, which gives us what? 0.3. Is my point well made? Oops. Hello, is my point well made?
Yes, please.
Okay, so likewise, we can get what? P, okay, so B, that will be therefore P, okay, Kweku will not pass. So Kweku will not pass. Okay, let me clear what we have there, then come and continue there. I hope you are following.
Yes, please.
Great. All right. If you have any question, please don't hesitate to let me know. Okay, so will not, okay, pass an exam, or the exam. Was it D? Okay, so D, exam. Okay, will be equal to 1 minus what?
0.8.
Okay. All right. So you know, instead of writing the notation now, you know, so you can write 0.8 there, and that gives you 0.2. So as you mature, this step can be skipped always, and you can do it mentally. Okay, very soon you will see where we will make use of this, okay, often. Very, very, okay, important. We'll be looking at situations where your presentation must follow exactly this form, and you use it to answer some other questions. Okay, any questions before I move on? We are all fine. Okay, so if that's the case, then we thank God. Okay, we are through with maybe our first session. Let's go and have a water break. Okay, so you are welcome back from the water break. Okay, so we are going to look at another set of special events. Okay, and we'll be dealing with compound events this time around. Okay, so probabilities of compound events, but you need to know the various compound events that you are likely to encounter. And here, when we mention compound events, it means you can see that so far we've been dealing with simple events where you are asked to find, okay, probability of a certain event with no connector. Anytime you are asked to find probability with connectors, either or and, okay, then it means you are dealing with compound events. And every compound event, okay, be it or the end situation, has a way of dealing with it, and that's what we are going to look at. Okay, so the first set of compound event that we are going to consider, which also will be more or less types of, or should have been treated under the types of events, okay, will be mutually exclusive and non-mutually exclusive events. These two, if you know one, you know the other. Okay, and again, okay, you can see even union and intersection. So this goes to establish the fact that probability basically connected with what sets strongly. Okay, so non-mutually exclusive events are events that can, happen at the same time. Okay, so the event that can happen at the same time, or events that will have the same or some outcomes in common. So in terms of a situation where your event, you know the outcomes, then it means you use the outcomes to determine whether the events are mutually exclusive or not. When you have two events and you realize that you have more or less an outcome, in at least an outcome in both events, more or less an intersection, then it means you are looking at the event to be a non-mutually exclusive event. So here we say that is two events A and B are non-mutually exclusive if they, this shouldn't be there, should have been, they have outcomes in common. Examples include getting even numbers and prime numbers on a die. And you can see that if you list the set of even numbers, so your first event, let me consider this as my first event quickly. Okay, so I am looking at my event, my first event. Let me use E sub 1 as my first event. And that is the event of getting, even numbers, when you, roll a die. Okay, what do you have? Even numbers on a die will give us 2, 4, 6. Am I right? So your second event, I'm using E sub 2 to represent the second event. It could be A or B. Okay, all right, then now what do we have? Prime numbers. So getting prime numbers, list your set of prime numbers for me. When you on a die.
2, 3.
Okay, 2, 3, 5. So this is what you have. And if you can see that with these two events, you know the outcomes. Do you see any outcome common to the two events? Okay, yes, you see 2 to be common. So immediately this occurs, then it means your two events are regarded as a non-mutually exclusive events or non-mutually exclusive events. Is that clear?
Yes.
Okay, so basically when we talk of under sets, when you have two sets to have an outcome, at least an outcome in common, you can, when you are drawing the circles representing or the Venn diagram, usually you draw it in such a way that the two circles will overlap. Is that not it?
Yes.
And that is exactly so here. So you can see, that is exactly so at that particular point. So here, when it comes to sets, we'll call these two intersecting sets. However, when we come to probability, it will be intersecting. What is the name given to sets under probability?
Event.
Events, as simple as that. Is that clear? So another name will be intersecting what events. And please take note, let me start from the set perspective. In set, especially in two set problem, which here we are looking at two events. So in two set problem, this formula, I know you know, rings a bell. So we say that if you have A union B, that's the number of A union B, will be equal to, you remember this formula, the number of A, help me, plus the number of what, B, let's go, minus what? The number of A intersection B, do you remember? And this is the formula in terms of sets. However, when you are dealing with probability will always have a denominator, and the denominator will be the number of sample space. So if you divide this one by the number of sample space, that's the number of S, each of them, the number of S, you still keep the equal to, because in maths, whatever you do on one side of a relation, you do same. So it's like you are dividing both sides by number of S, so over number of S. So the number of A union B, you know that, and the probability, the number of what any event over the number of what the sample space will always give probability of the event. Is that clear? So it means this will give us the probability of the event A union B, which must be equal to, this will also give us the probability of the event A. Then plus, this will give us probability of the event B. Then this gives us what? Minus probability of the event A intersection B. All correct?
Yes.
Okay, so this is where this one is coming from. Okay, so anytime you read any probability question and you see or union, okay, it means the question wants you to make use of, okay, what we call addition rule, or mutually exclusive and mutually exclusive. Okay, we'll look at the mutually exclusive, and after that, okay, I'll put these two together. Okay, there is another formula that will come, and we will consider these two formulas. Okay, we'll consider it under one umbrella and give it a name. Okay, very soon. So indirectly, I've explained that of what? The non-mutually exclusive. Can I move? Sorry, the mutually exclusive. Can I move on? If you know mutually exclusive, you know non-mutually exclusive and vice versa. As simple as that. So now that we've learned, okay, or we know, okay, non-mutually exclusive events, you should know the definition for the mutually exclusive. So if you don't have any question, let's move on. Okay, so mutually exclusive events. So if we said, okay, the mutually exclusive events will be the events, okay, that can happen at the same time. Okay, then it means that mutually exclusive will be the situation where they cannot, okay, happen at the same time. Okay, we said non-mutually exclusive, you should have outcome or outcomes in common. For mutually exclusive, there shouldn't be any outcome in common. So it's the same thing. They have no outcome or outcomes in common. For example, getting a head or getting hairs and tail in a coin toss. There is no way you can get a head that is also a tail. Okay, or if you are looking at what your first trial, head and tail. So your first trial, the success that will be head and tail. So your first event, head and tail. Okay, your second event, we are looking at what? Getting even numbers. Okay, so maybe if I'm looking at even numbers, my E sub 2, E sub 1, even numbers will be 2, 4, okay, 6. Okay, these two outcomes, do you see, these two events, do you see any outcomes in common?
No.
No. In the same way, I can mention, okay, that if you are looking at this time around a die, okay, your first event is getting even numbers, which will be 2, 4, 6. If your second event, okay, the same die, your second event is getting odd numbers, that will give you 1, 3, 5. Do you have any outcomes in common? Hello? Okay, so how would you term these two events? Mutually exclusive or non-mutually exclusive?
Mutually exclusive.
Mutually exclusive, because they don't have any outcomes in common. So in this case, under set, what will be the name given to sets that are not overlapping? Okay, that you can't see any outcome in common. This name is for probability. Under set, what will be the name?
I think disjoint.
Perfect. Disjoint. So under set, we call okay, such sets, okay, disjoint sets. However, the probability sets are events. So in that case, what do you think will be, in natural fact, it's supposed to be disjoint events. So disjoint, okay, event. That is supposed to be here. Is my point well made?
Yes.
Okay, and in the same way, this you can relate, just as I explained the other one. If you go back, okay, the other one, with the mutually exclusive, because there is no intersection, the probability here will be 0. Because your number of successes will be 0 over your number of s. And once your numerator is 0, okay, the whole of that fraction will be 0. So for mutually exclusive, this last term, okay, in the formula will go. So you'll be left with only the first two terms. Point well made.
Yes.
Just like set, if the intersection is not there, okay, the last, okay, term will go. because it will give you 0. So this is where the formula is also coming from. So if you are fine, then let's move on to where it will be considered under one umbrella. So here, this is it. Okay, so the two rules that you were just introduced to, one for non-mutually exclusive and one for mutually exclusive, okay, will be what we call the addition rules. Okay, so anytime you see or, you see union, okay, linking two sets, in this case events, then it means your mind should be focused on the addition rules. And the addition rules, we have two, the first one or the second one. Okay, if you settle on the first one or the second one, then you have to make that determination as to the type of what events that you are dealing with, whether mutually exclusive or non-mutually exclusive. Non-mutually exclusive means you have to quote this one. Mutually exclusive means you have to close or choose what this one. Okay, so please take note. Non-mutually exclusive, you go for the first one. Mutually exclusive, you go for the second one. So quickly, let's look at, okay, the following what questions. All right, any questions before we start handling what we have before us? The first worked example under the mutually and non-mutually exclusive event, our first compound event. Hello, are we fine?
Yes, please.
Okay. Okay, all right. So now let's see what we are supposed to do in terms of our solution quickly. Okay, so obviously solution is what you write first. Your question number you extract. So I have extracted just to save time. Okay, so that is what we have here. And let's see what we are going to do. Okay, so given, or in this case now I've taught you that you can straight away, because the question asks you to find P of A, you can straight away write therefore here. If you write given, then you have to draw your conclusion. Is my point well made?
Yes,
Okay,
please.
all right, so you should know. So in this case, if you want to go by our usual rule, okay, P of A will be the number of elements, in this case outcomes in A, over the number of outcomes in the sample space. So what will be the number of elements in A?
4.
Outcomes 4, so it will be 4 out of what? The number of outcomes in the sample space, 10, am I right? So
Yes.
that gives us 2 over 5. In this case, therefore will be here, so we won't draw our conclusion. However, if you write given, then you have to write therefore P of A will be equal to what? 2 on 5. Is that clear? There
Yes.
shouldn't be 2 therefores in the same question, so please take note. Okay, all right. So now what do we do? B. Okay, so B, if you cancel this and put therefore there, okay, P of B will be equal to, you count the number of elements in set B. In this case, the number of elements in event B, and the number of outcomes, sorry, in event B, and that will give us 3 out of what? Again, 10. This cannot be reduced, so this then becomes your final answer. Afa? Okay, and last but not the least for, okay, the I, we are looking at what? P of C. So probability of getting a C, you count 1, 2, 3, 4, 5. So you get 5 out of 10, which can reduce to what? 1 out of what? Out of 2. All correct?
Yes.
Great. Okay, so now we are going to move on to maybe where you can see certain. Okay, so quickly, let's go. Okay, A intersection B means you have to go and look for, okay, the outcomes of A intersection B. Okay, so let's look at A and B. A and B, okay, how many outcomes do you see in common? Do you see any outcomes in common?
No.
Okay, so that will give us 0 over your number of S, which is what? Which will give you 10. But you should know, as you mature, that will give you 0 straight away once there is no outcome. So this gives you, okay, 0. Okay, is my point well made? So this
Yes.
goes to establish that, okay, in this case, what will be the nature of your events? A and B, are they mutually exclusive or non-mutually exclusive?
Mutually exclusive.
Mutually exclusive. Okay, you take note. And remember, therefore is what you put here. Otherwise, you have to come and draw your conclusion. Okay, so let's move on. The next one, A intersection C. A intersection C, A and C, do they have outcomes in common? I can see 3 of them, right?
Yeah.
Okay, so the number of outcomes in common will be 3 over, so the number of A intersection C over 10. So that will give you this. Okay, so again, you can see that A and C are non-mutually exclusive events. Okay, so now let's go and see what, in actual fact, we are supposed to know in terms of what we just learned. As for B and C too, you can get it. B and C equally are non-mutually exclusive, so you should be able to calculate the corresponding probability. Then now, let's go and look at the union. Okay, we'll handle this from 2 perspectives. Okay, one using the addition formula that we just learned, or the addition formulas that we just learned, and one using our usual technique, which is the number of what your successes over the number of what your sample space outcomes. All right, so first of all, let's go our traditional way. We know the outcomes, so you have to go and find the number of elements, or outcomes in A union B. So you have to find A union B before you count. So let's do A union B. Okay, we are doing this as more or less a rough work. Okay, A union B will give us the set
1, 2, 3, 4, 5, 6, 7.
4, 5, 6. Is that not it? 7.
7.
Okay, so if you count, how many do you have? 7. Over your total, which is still 10. Is that clear?
Yes.
We are going to do same here. Then after that, we go and look at the alternatives together. Okay, A union C. If you look at A and C, okay, so A union C will give us
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5. Okay, there is no 6, so 7. Is that not it? So if you count, we are going to get 6. So you get 6 over 10, which can be reduced to 3 over 5. Point well made.
Yes.
Okay, very good. So at this point, we are going to look at the alternative approach to this. So alternative approach. Okay, I've told you that anytime you see union, okay, or you see or linking 2 events, A and B are events. Other than that, you cannot, even unite them. Okay, so once they are events, okay, and being linked with what? Union, which is the same as or. Okay, it means we are supposed to settle on one of the addition rules. So here, the addition rule that you settle on will depend on the nature of the event, mutually exclusive or non-mutually exclusive. So now let's go and see A and B. Are they mutually exclusive or non-mutually exclusive?
Mutually exclusive.
Mutually exclusive. So it means if you are quoting the formula, so alternative approach, you write therefore P of A union B, okay, will be equal to, if you are quoting the formula, it will be P of A, okay, plus P of B minus P of A intersection B. Is that clear? Am I right?
That one is for non-mutually exclusive.
Very good. So it means you are following. Okay, so in this case, the third one shouldn't come, because you've already made that determination that your 2 events are mutually exclusive. So this shouldn't be there. If you write it, you still go and write 0 there, which will waste your time. So quote the formula that will save you time, and therefore your work will save you time. So in this case, so you can see that the mutually exclusive one is a special situation for the non-mutually exclusive. The non-mutually exclusive formula is a general formula. But the special situation where there is no intersection, then it becomes the mutually exclusive. So in this case, I can come down and write equal to, what is your P of A? What did you get as our P of A? Remember, we've done that. P of A gave us, okay, 2 on 5, and P on B gave us 3 on 10. So when we get there, we are going to write the values there and see. Okay, so this gave us what? 2 on what?
2 on 5.
Okay, then plus what? 3 on 10, am I right?
Yes.
Okay, so are you sure? Okay, so this is it. So now we are looking at what? The sum of the two. So if you sum, what do you get? You are supposed to get 7 over 10.
Yes, please.
So it's the same thing. So you see the validity of what? The addition rule for the mutually exclusive. Okay, now let's look at, okay, the alternative for this. Okay, however, in this question, okay, it is better once you know the outcomes, okay, you can use this method or that. Okay, however, this method will be anytime you know the outcomes, it's convenient to use this method. But this formula here will be very useful when the outcomes are not given, but you know the corresponding probabilities. Okay, so in this case, maybe you'll be given P of A, P of B, P of C, and you'll be asked to find the whole of this. In this case, you don't know the outcomes, so the only option will be this. So very soon, I will give you questions that you can only use this particular method. But I just want you to know the validity of what the rules. That's why I gave you questions of this nature where you can use the two at the same time. So let's go. Therefore, okay, P A union C will be equal to, let's quote the formula.
Mr. Ackman, please, is A union
A
C.
union C, forgive me. Okay, this is not intentional. Okay, so now, what the A union C, the two events, okay, we are uniting, so it's all here. Let's determine the type of events and use it to quote our formula. The A and C, are they mutually exclusive or non-mutually exclusive?
He is non-mutually exclusive.
Okay, so non-mutually, so it means we are going to write the formula as P of what? A plus P of B, that is not all. The third term should come. P of the intersection of the two sets, or in this case, events, so A intersection C. So that gives us, okay, you know the values. We've done P of A, and that gives us what? The 2 on 5.
2 on 5.
Okay, then plus P of B, we also know that gave us 3 on 10. We did minus P of A intersection C. Yes, please.
This is P of
Oh,
C.
P on C. Sorry, forgive me. Okay, so thank you. All right. I don't know why I'm writing B like that. Okay, so now what do we have? So the intersection, we've done that already.
Mr. Ackman,
Okay, so this is P of C. So I'm waiting for the P of C answer. What did you get? We've done
this
that.
is 1 on 2.
Okay, so this is 1 on 2. So let me do the correction. This is 1 on 2. Take notes. Okay. If you are the one, you cannot dip in. You have to cancel it and write it again. Is that okay?
Yes, please.
Okay, you avoid deepening your. So the intersection C, you have it. So call your answers for me.
3 on 10.
3 on 10. Okay, and if you like, combine this using your calculator straight out. You have to get 3 on 5, the same as what we have here. All correct?
Yes, please.
Okay, any questions at this point? Hello, any questions? All right, we thank God. Okay, so now let's move on to, so this one, you should be able to do it. Okay, and okay, this is going to be probably our last, okay, question. Okay, maybe if time allows, we'll look at another question. Okay, I wanted to give you that question as a weekend challenge, but we can still, if you're able to finish probability, okay, you are doing well this vacation, both core and relative, I will be very grateful and happy. All right, so let's look at question 2. Okay, a box contains 3 glazed donuts, okay, 4 jelly donuts, I think I'm whetting your appetite this morning, and 5 chocolate donuts. If a person selects one donut at random, so selection is fair, find the probability that it is, okay, A, either a glazed donut or a chocolate donut. So you can see the connector here. Can you see that?
Yes, please.
So immediately you see, oh, what have you in this case, the situation so far? Okay, then you are dealing with compound events. Your first event will be this, that is getting a glazed donut. Okay, then your second event will be getting a chocolate or donut. Is that clear?
Yes.
Okay, very good. Okay, so now we'll do the A together, then I'll ask you to do the B and C probably as your homework. Okay, all right. So let's go and look at how best we can carry out our presentation, which is key. So please take note of how I present my solution. Okay. Once my solution presentation is okay, ideal to you or nice to you equally, if you write it, it will be nice to everyone. Okay, so now quickly let's go and look at the solution, okay, to this particular question. Okay, a box contains 3 glazed donuts, jelly donuts. Okay, so here it will be better we equally get a representation for our event. Okay, and the event, you can see 3 donuts, jelly donuts, so you can see counts. I hope you get it in terms of number. Do you get my point?
No.
Okay, if I say 3 donuts, how did you get the 3 donuts? Definitely you will count. We are talking about the number of donuts. You get it?
Yes, please.
So this question is dealing with, in a box, you have a certain number of donuts, okay, of which 3 of them are glazed, okay, 4 of them are jelly, and 5 was chocolate. So these are the flavors. Is that clear?
Yes, please.
It's clear now. So with this one, okay, look at how I'm going to do my representation. Let's go back to the previous one so that you can get the connection. How we did the representation in the previous one. Not here. I have to go back a little more. Okay. Was it the other one? Hey, with this one, you can see that you were giving probabilities that, Amma, can you get any number here? Do you know any counts? Okay, so in that case, when we're getting our representation, though we said the representation is necessary, we realize that, okay, putting the representation in curly brackets, okay, is not the way to go because you are not dealing with a set for you to know the number. So in that case, the curly brackets will not be necessary. However, here we know the number. So when you are getting your definition, treat what you have there as a set because we can get the count. Point well made now. So we are going to use let. In set, usually we want to define our universal set first. Is that not it?
Yes.
Okay, what is missing in my presentation so far?
The question number.
Perfect. Okay, so equally, I know that when you are giving your presentation, okay, you will not, okay, leave out the question number. Questions are numbered, your solution equally must be numbered. Okay, so thank you very much. So you write what question number 2 here. Okay, and you write let's. Okay, then our S will be in all we are dealing with donuts, am I right? A set of donuts, yes. So donuts. Okay, then here I use curly brackets. Okay, because I'm dealing with a set because I know the number. So don't do away with the curly brackets. So I've told you, normal always when you are getting your definition, you put it in curly brackets. Okay, then let's go. Okay, comma, our first set, maybe or the next set, okay, which will be your events, will be this their sample space, okay, which is a special event anyway. Now let's look at the other event. So we will use, okay, G, capital G, okay, to be glazed. So I can choose not to attach the donuts because I'm dealing with donuts anyway. If you like, you can attach. Then the other one will be J. And you can see that I'm extracting my information in row just to save some line. If you extract it in columns, you use more lines. Okay, so jelly, donuts, and the last one, okay, C, capital C will be for a set of what? Chocolates, okay, donuts. Okay, so it's better you deal with it that way. Are we fine?
Mr. Hartman.
Yes, please.
So please, does it mean if they give you a question and like you are sure of the number of um items you've been given, you put it in a curly bracket?
Yes, you define it as a set. It's only set that we can get the numbers. So
Okay.
your definition should appear as a set, so that when you are extracting your data, you can use the numbers. So this implies that the number of your S, you get it, which is
Yes.
your set. Usually we use this for set. You get it.
Yes.
So that's the meaning. Okay, well done. Okay, at least I think you have gotten my drift very well. So number of S. Okay, what do we have? You sum everything together and that will give us 3 plus 4 plus 5. 12. Okay, 12. Okay, number of G, glazed donuts. How many? We have 3. Okay, number of what? J, jelly donuts. How many do we have? We have 4. And last but not the least, okay, the number of what? Chocolate donuts. We have what? 5. All correct?
Yes.
So it means the information given, okay, here is what we have extracted mathematically here. So now that we are going to solve the question itself. Okay, so let's go. Okay, A. A, we are looking at probability either a glazed donut or chocolate donut. So I'll write, okay, therefore, P, okay, glazed donuts. You can use the letters, okay, only that if you use the letters here, you can't use therefore, remember, because you don't conclude with what you introduce. That's the more reason why I'm starting with. Then later use the letters if need be. And definitely there will be the need. Is that clear?
Yes.
So glazed donuts, okay, or okay, chocolate, okay, donut. Okay, so this will be equal to, we can see the connector here, or, so it means we need to determine, okay, whether the two events will have outcomes in common. And here, do we know the outcomes in the events? Do you know the events, but do you know the outcomes?
No.
You don't know. So when you know the outcome, that's where you use, okay, this way of determination. Check the outcomes, the events, if they have outcomes in common, then, okay, you will say that the two events are what? Non-mutually exclusive. Otherwise, they are mutually exclusive. However, if you are not able to use the outcome, that's if you don't know the outcomes, that's where you use the other one. We use the can happen at the same time and cannot happen at the same time. So in this case, because we don't know the outcomes, we are supposed to use, okay, this event and this event, can they happen at the same time? If they can happen at the same time, then it means, okay, it's like I have two balls maybe colored separately, one with distinct colors, maybe one is blue, one is green. Okay, go into the box and pick what? Any color. Okay, is it possible for me to pick a ball that is green and at the same time blue? Is it possible?
No, please.
No. So that means they cannot happen at the same time. Okay, again, in this case, do you have any information about, okay, in terms of the flavors? Okay, we have glazed, either you have only glazed or only chocolate. Can you have, okay, a donut that is glazed and chocolate at the same time? Look at the question carefully. Can
No,
you?
please.
No. So it means the two events, that is the glazed donuts and chocolate donuts, cannot happen at the same time. It's either your donut is only glazed or only what? Chocolate. Is that clear? So once they
Then
cannot happen at the same time, then we know the type of events. Which events are we dealing with? Mutually or non-mutually?
mutual.
Mutually. So that will give us indirectly what we have here. I can now use the letters. So it will be PJ, okay, or okay, C. And because I'm dealing with what mutually exclusive, it will just be PJ, okay, plus PC. Is that clear? Is my point well made now? Hello, my professors, are you there?
Yes.
Okay, are you following? You are there, but are you following? Okay, I should repeat it from where?
P, G, or C.
Okay, so you know that J is for glaze. Can you see? So I want to use the letters now. I could have, like I said, I could have started with the letters from the beginning. But if you start with the letters from the beginning, you cannot write therefore. Because if you write therefore and you don't conclude, you are concluding with what you have introduced. You get it?
Yes, please.
So J is for glazed donuts, then C is for chocolate. So it will be J, your or is there. But anytime you have two events connected with or, it is the addition rules that should come to mind. And the addition rules, you cannot use two at the same time. You have to settle on one. And that means you have to make the determination mutually exclusive and non-mutually exclusive. And we've done a lot in terms of the determination. The two events cannot happen at the same time. You cannot have a glazed donut and at the same time chocolate donuts. So it's like you don't have a cocktail, sort of. You get it? You don't have a mixture
Yes, please.
of the flavors. So in this case, for the rule, addition rule, when it is or, it is the probability of your first event plus the probability of your second event, okay, then minus the other one. But because they cannot happen together, the minus will give you 0. So you quote this one, which is for the mutually exclusive. Is it clear now?
Yes, please.
Okay, so now you are good to go. This is your probability. You know the numbers. So the number of J, what do you have? 3 over the number of S, okay, which is what? 12. Plus the number of C, what do you have? 5 over the number of S, that is 12. So this gives us, you add, and that will give you 8 over what? Over 12. And this gives you, you can reduce, so 4 over what? Over 6. Oh, sorry, you can, forgive me. You can reduce more. Okay, so so this will rather give you 2 over 3. Is that not it? Hello, is my point well made?
Yes, please.
Okay.
please.
All right. So if you don't get it, let me know because I'm not going to go further. I'm going to end here. The B and C will be yours. Okay, to deal with. Any points? Okay, someone equally can move from here, okay, to this. So if you are smart and later as you solve more probability questions, you get to know once we are looking at this or that, it's just a matter of summing the two. Okay, so you sum the 3 and what and the 5, then you divide by the total. Okay, so somebody can write here is equal to 3 plus what? Plus 5 all over 12, which is exactly the same thing. But if you separate it this way, you know that you are going strictly by the rules or the formulas. All correct? Okay, so if that's the case, then we are going to what? End here. Okay, we are going to end today's lesson here. We thank God for once again a successful lesson.